In this video, we'll be using lasers to help us understand the wave nature of light. We're going to start off by looking at diffraction. So what is diffraction? So, if we have waves and they're travelling in a plane, so they're travelling at a constant straight line towards an obstacle. When it hits this obstacle, it can cause these waves to curve. So they change the direction of their propagation. So this is diffraction. If we have a straight line of waves going towards an obstacle, and when it hits an obstacle, they curve around it, that's diffraction. So an example of this, if you're standing behind a corner of a building and someone's making some loud noises on the other side of this building, the sound travels around the corner of this building. We know this. We've seen this from years and years of experience. Okay, so if that's diffraction, if we look at diffraction through a slit in something, so we have a plane of waves going towards a slight hole or a slight vertical slit in an object, we can get that these waves curve around this slit as they go through it. So the amount of curvature that we see in the waves is dependent on the size of this slit. So the closer this slit is to the size of the wavelength of the light or the wave that we get going through this slit, the more diffraction we see. So the better diffraction happens when we have a slit that is comparable to the size of the wavelength of the wave. So diffraction is the curvature of a wave, and if we have a slit in an object and we have a wave going to this object, this slit can cause the waves to curve when it passes through this slit, and the more curvature we see depends on the size of the slit compared to the wavelength of the wave. Okay, so we're going to be looking at an example of this. We're going to have a laser going through a single slit, and then it's creating its interference pattern on the wall. So, you can see on the wall here this pattern. I have the interference due to a single narrow slit. So my laser, or my light source, is got waves hitting this single narrow slit. As these waves hit the single narrow slit, we then have diffraction. This diffraction curves the waves, causing this interference pattern that we see on the wall. So we can see we have a wide central point of maxima. We then have little points either side of this, which are less intense than this middle one. There's gaps in between each of these points. These gaps are approximately equal size. So if we graph what we see on this wall here, we would get something like this. So we have the central point which has the most intensity, and then from each of the gaps we get the other points of light, and they reduce in value as we move along. The further away from the central, the less power we have, or the less intense the light is. So you saw the interference due to a single slit. Now let's create two slits very close to each other. We can measure the gap in between them, but it's going to be very close. It's going to be approximately maybe 1/4 of a millimeter. So we're going to have our laser light source going through these two slits at the same time, and it's going to create an interference pattern on the wall. The wall's several meters away from our slits. So you can see our interference pattern on the screen here. So we have that there's dark fringes and there's bright fringes. So this is a interference due to a double slit. So the light's going into the double slit and it is diffracting, causing this interference pattern you see here. In setting up our experiment, if our light source that we use is not a monochromatic coherent light source, then we need to use a single slit. The single slit ensures that when the light passes through it and reaches the double slits, the light hitting the double slits is coherent. We want our light to be in phase. If our light is not in phase, then we're going to have issues getting our interference pattern how we want it. So we need to ensure that when the light source hits our double slits, it is in phase. It needs to be coherent. So, the experiment setup that we have. So, my experiment setup that I have here consists of a laser. So this laser is a monochromatic light source. So this laser is then passing a beam to double slits. It's directly going to the double slits because the light source is going to be coherent. So, as it hits our double slits, the double slits then have their diffraction pattern happening, and when we reach our wall, which is several meters away from our double slits, and the double slits is about a meter away from our light source, we get that the interference patterning happening that has the dark and bright spots with maxima points. So the experiment setup is a light source. Depending on the light source depends on if you need to have a single slit. If you've got a coherent light source, then you don't need to have the single slit, but if you don't, you need to have a single slit directly after your light source, and then your double slit's about a meter away, and then your screen several meters away from that. So that's how you set up the experiment for Young's double slits. So, how does double slits work? So we have our coherent wave source hitting our double slits. These double slits then produce two diffracted wave sources. As these diffracted two wave sources move away from the double slits, the same thing happens when we have our two points of wave sources that I showed you in the other video. So we get this pattern happening. So we get this curvature, or the diffracted waves, which then interact with the two waves. Where the crests meet another crest, we're going to get an interference where we have constructive interference. So this constructive interference leads to producing a bright spot. So on our screen, wherever we see bright spots, we're going to have this constructive interference. Wherever we have a trough and a crest interfering with each other, we're not going to get any light at all. It's going to deconstructively interfere. So this is going to be where our dark spots are. So if we draw up the pattern, and we can see the overlaps, wherever we have a bright spot, we have the constructive interference. Wherever we have dark spots, we have deconstructive interference. So this is how double slits work. Very similar to our 2 points of waves that I showed you in the last video. So, our pattern that we have here, we got our bright and our dark fringes. So, if we draw a graph of these bright and dark fringes, we get a pattern that looks like this. So this pattern shows you exactly where our maximas are, where our bright fringes are, and where our minimas are, or our dark fringes. So what's causing our bright and dark fringes? So our bright fringes are where we have constructive interference. This constructive interference is where the path difference between our two slits, so the two wave sources from the two slits, is going to hit the screen, and the path difference is within a m lambda wavelength. So the path difference is going to be within a wavelength range. Wherever we have our dark fringes, this is where we have deconstructive interference. So this deconstructive interference happens when we're going to have half a wavelength difference in the path length that it took for one wave and the second wave. Wherever we have this, we're going to have deconstructive interference. So that's how we get our bright and our dark spots in our interference pattern on the wall or the screen. So it's going to have a wavelength difference or half a wavelength difference. There's a couple formulas that we need to know. First of all, how to derive and how to use. So how to derive these formulas, I'll show you in a LiveScribe PDF. And also how to use these formulas. So these formulas are d sine theta is equal to m lambda, and delta y is equal to lambda L on D. So we need to be able to use these formulas, and you need to be able to derive them. For ease of myself, I'm going to be showing you this on the live scribes, because it takes a lot of work to show you how to derive a formula in one of these videos. A lot of work. So, the key points from the video today. Single slit interference is caused from a diffraction. Diffraction is the curvature of a wave. So we see the single slit interference with a bright spot maxima, and it slowly goes off when you get to the edges. So we get bright fringes and sort of dark fringes. Double slit interference, we need to know how to set up the experiment. So the experiment is we have a monochromatic light source which is coherent hitting the double slits. If our light source is not monochromatic or coherent, we need to have a single slit first. So we have a light source, single slit, double slit going onto a screen which is several meters away. We need to know the formulas. D sine theta is equal to m lambda, and delta y is equal to L lambda on D. Also, the double slit interference pattern, you need to be able to describe what this interference pattern looks like. So the interference pattern looks like you have the waves from the 2 points like I showed in the last video. So we have the light source hitting the double slits, and each of the double slits is producing a curved light pattern, a curved wave pattern. Wherever we have crests meeting other crests, we get constructive interference in this. Wherever we have a crest meeting a trough, we have deconstructive interference. And this leads to our bright fringes and our dark fringes on our screen. So wherever we have interference that's constructive, we have the bright spots. Wherever it's deconstructive, the dark spots. So hopefully you learned something about the interference of light.